Thank you, everyone. As you said, my name is Bill Johnson. I am a Principal Engineering Manager at Azure SRE. SRE stands for Site Reliability Engineering. And for anyone that's not familiar with that discipline or that role, at a really high level, SREs essentially find engineering solutions to operational problems. And so some of the ways that we measure that work is through latency within a system, reducing the latency within it, the level of availability or how many errors there are, and how much is acceptable for customers. If you hear the term of how many nines a service can support, that comes back to reliability, throughput of the system, and then also any saturation that can come in from data storage or bandwidth or anything. My role specifically is leading site reliability engagements, and those are temporary, on the order of months or years of time, where we go, me and a group of engineers go and embed ourselves with an Azure service. And our focus there is not about building new features. It's not about creating a bunch of new code and new stuff, functionality. It's about focusing just on the reliability aspects of the system. So those things I just listed off: the latency, the availability, the throughput, the saturation, and really trying to improve the reliability of the system itself. So I feel like I said reliability like 5 or 10 times there. What does that actually mean when we say reliability? At the end of the day, is the system there when you need it? Can you depend on it to be available, to be usable for a customer, for you as an engineer? If it's there, can you trust that it's going to do the thing that it's supposed to be doing? And then even more specifically, if it's there and it's doing what it's supposed to be doing, is it doing it in a way that is performant and is meeting the standards of your time? If a customer is expecting something to be ready or completed in milliseconds and it's taking minutes, that's a huge issue. And so that's where we come in and really focus on these reliability aspects of a system. Similarly, on the sustainability side, kind of when we say sustainability, what does that mean? Is this something that you can maintain over time? Is this a process or a power source or a set of code that is able to be maintained? Is it durable enough to withstand changes, to withstand outside influences or forces? And then can it adjust on the fly, or can it be tolerable to changing conditions? And so you don't have to completely rewrite something or completely redo something because one of the factors has changed. So traditionally, these two fields, so reliability and sustainability, these two concepts and fields have been very separate, and they don't really overlap as much. They kind of do a little bit. But at the end of the day, I feel very strongly, and my goal here is that sustainability and reliability are very similar. And in fact, sustainability sometimes can be defined as reliability over time. And as an SRE, our focus is really about creating reliable actions within a service over an extended period of time. One of the reasons we do engagements is that the goal is we should be able to go to a team in a limited amount of time, set up reliable systems and infrastructure and tools that can then exist without the presence of us. And then we can focus on another area of that system or another service or another part of Azure entirely. So really it's about reliable stuff, but sustained over a long period of time. So let's dive into a little bit of the sustainability side of this. I break this down into kind of 3 big areas of sustainability. And that first one is really about the technical components of a system. So what are the choices? What are the things that go into a system from a technical perspective that you need to maintain and be true over a long period of time? So, what types of CPUs or hardware or servers need to run in order to support your service and your system? What does that network look like? What types of programming languages do you choose? Is it a compiled language that needs to be built and it takes 6 hours to build it and deploy it? Or is it a scripting language that can be done on the fly? Or is it just basic HTML that you can not even have to upload and just save right there on the server? Those are all technical choices that we make, and each of those choices that we make in the system has some level of sustainability that's tied to it. The second level of this, from going from technical, is once you've made these choices, someone has to maintain these choices, right? Someone has to operate them. Someone has to push the buttons, and someone has to answer the calls when customers, submit cases and incidents. And so this operational level of sustainability is, what's the human toil? What's the human aspect of this system that goes into it that you need to maintain, or that whoever is in charge of the system needs to maintain? this is a lot of the stuff on the SRE side that we focus on as well. So, that on-call burden for an engineer that's going to get paged in potentially the middle of the night, do they have the right data in front of them, the right observability into a system to be able to make decisions for that system in order to save the customer experience so that customers aren't impacted as much as possible. How do you learn from those things going forward? It's not always just technical decisions. It's when something goes wrong, how do you break that problem down, learn from it, and apply those learnings forward so that those things don't happen again, or at least happen in a very different manner. So technical, operational, and then this third level of sustainability is probably one that we're all very familiar with here, is all of these things that we do from a technical and operational aspect have an impact on the environment, have an impact on our planet. We can measure these in any number of ways that have been touched on quite a bit today. So, PUE, carbon emissions, all scopes of those, carbon triggering, all these types of things fall into this environmental sustainability aspect of how are we impacting the planet based on our choices that we're making within the software. So these three areas, technical, operational, environmental, sustainability, they all exist and they all need to be operating in some balance. In the past, or traditionally maybe for software engineering, we focused very, very heavily on the technical. Can you just build a system that is now creating a thing for a customer to be able to do it? The Uber that was mentioned in the last time, Uber is a technical choice that was created to build and support the use case of someone needs a ride to get to somewhere, right? Those were all technical decisions that were made. And software engineers typically live and focus on that aspect. That's obviously not sustainable. And 5 or 6 years ago, Google introduced a new discipline called site reliability engineering because they found that the operational aspects of a system were far outweighing the technical ones. And so that's where SREs were essentially born, was to make the stuff that already exists work. Their goal is not to create new things; it's to make things that already exist that much better and easier to maintain, so that we can then do even bigger and better things. And it's really that balance of technical and operational sustainability that SREs focus on. And so similarly, when we start to incorporate the environmental sustainability into this, that's where the sustainable software engineer comes in, is that balance across all three. You can't just focus on environmental pieces because the technical and the operational pieces will get unduly affected. Similarly to how the software engineer was traditionally thought of, is just focusing on the technical side. Conveniently, there's a concept we can borrow from economics and game theory called Pareto optimal, or Pareto optimality. And that Pareto optimal point is in a game is where no other player within the game can get more of a payoff without decreasing the payoff for another player. And so it's about finding that equilibrium. And that's really where that sustainable software engineer comes in as a balance, to find that equilibrium point of all three of these levels of sustainability, so that everyone benefits equally, not necessarily equally, but so everyone is at this nice equilibrium point to go forward with. And that's essentially how SREs operate between the technical and the operational sustainability too. We can't go fully in on operational, we can't go fully in on technical. It's about finding that equilibrium, that balance point in between for the right level of availability or latency. And so at the end of the day, this is really just about the balance, right? There's a lot of things that come into play. There's business rules that need to be followed. There's compliance that comes in. There's government regulations. There's various customer behaviors that can drive and influence these things. And so that balance of these three areas is the key for sustainable software engineering. So what do we really mean about this? To go through a few kind of tangible examples here. At the end of the day, when we're talking about is really efficiency. If you can narrow it down into a single word or a single concept, it would be efficiency. It's, using the least amount of resources necessary to do the thing you need to do. So designing your software in a way that is the most efficient, setting up your architectures, that's a way that's the most efficient. You can measure these things through, PUE is something that's been mentioned already today. I know is just how much energy is being consumed for computing. That's typically used for data centers. But a good concept to think about is, traditionally people will deploy large services out into data centers on a rack of machines and whatnot. If you've ever been in the mobile app development space, it's a very different world. And so you're running off of a battery, and every choice that you make can drain the battery. Every choice that you make and how many times you need to pull the Wi-Fi for your location or something like that has negative effects on the customer experience by draining the battery. And so it's a good way to kind of reset the problem, or rethink the problem. Is imagine you're developing this for a mobile phone. How would you do it differently? How would you use power more effectively? How can you approach that problem differently when you're constraining one of your resources? And then similarly, the compute utilization factor, or CUF, is another similar thing to PUE in that, but it's looking specifically at how well you're utilizing the compute that's available to you, and not necessarily the power. An interesting thing here is there's studies and data that's starting to come out now that's showing it's not necessarily 100% compute utilization. That's the goal, and it's really closer to probably that 70 or 80% where you want to stay. And that 70-80% is, again, going back to the balance of the benefit of getting that extra 5-10% of compute utilization is not offsetting the amount of processing power that you're getting from it, or the temperature that's being driven in there. And so again, to find that nice little balance point is the optimal place to be running your CPUs, typically around that 70 or 80%. So efficiency as a concept, what about on the hardware side? Roughly 75%, depending on the specific thing, but most servers and chips, CPU chips, roughly about 75% of carbon costs that go into it come from the manufacturer. And they don't come from the operational or the lifetime of it. So extending the life of the hardware that already exists still has the largest impact today. And so how can you extend the life of the hardware? So just talking about the CUF is, if you're running your processes at a slightly lower utilization factor and not overclocking them all the time, they'll last longer. And so that's one way as well to extend the lifetime of the hardware. You can repurpose any older machines. You don't need the top of the line machines for things that aren't your critical workloads in your system, right? Taking these old machines and reusing them for testing and validation system. You can create an entire test environment on, older or lower level machines that were at once your top of the line in production, but are now running there. You can set them up as an array of old machines for scaling up and scaling down, testing and validating those as your processes for scaling up and down, and where those trigger points are. And then one of my favorite ways is, old hardware is flaky, is going to be highly latent in some areas. And so use your old hardware as a chaos monkey at the end of the day. It's a really great way to inject failure into a system. It's a really great way to inject pressure into the system as take these things and build up just a chaos environment that's all the old machines, and you'll find some good fault injection scenarios over there too. What about the architectures of our system? So microservices, as just a real quick overview for anybody that's not familiar, there's kind of two architectural patterns. Of one is more of this monolithic, where you kind of build everything and deploy it all as one single system out. And then there's another architectural pattern where you can break that down into smaller pieces and deploy each of them individually. In the monolithic side, you're going to deploy onto a single server, or probably have redundancy onto 2 or 3 servers. Whereas on a microservices architecture, you may have 10 services that all intermingle and connect to each other, which would then have to be redundant. And so you're running 20 or 30, much smaller, but more numbers of machines. As we talked about before, the number of machines is a big deal. And so in a microservices environment, which is a very common pattern today, how are you going to go about looking to find that balance? The easiest one that we've already talked about is the compute utilization. If you've got 30 cores that are running now, or 30 CPUs that are running, maximizing the utilization of those is very important, and starting to grow and grow in the level of importance. Typically, each of these machines will have to connect to some sort of data store. And so optimizing that database is another critical component of this too. So if you're constantly scanning 1 billion rows on your request, can you add an index that reduces that to 10,000 or 100,000? Can you shard it across multiple different machines so that you're optimizing those requests and keeping those requests down? Don't need as much database storage space, don't need as much latency, so you don't need as much compute to process all of those rows. And then similarly, talking about latency is on the network side, optimizing that network traffic. When you have microservices now, you've got 10 different services that all need to connect to each other over different connectivity paths and latencies. Can you co-locate some of those and just put them on the same machine? Maybe they're in different containers, but all in the same machine. So it's all just local host traffic going back and forth instead of having to go out across the network and back. The good news is that across these three areas, you're essentially making your system more efficient, faster, and users will directly benefit from all these things. So not only are you increasing your environmental sustainability by reducing the emissions that are caused by your network and your database and the number of computes you have, you're also having your users benefit from a much faster and a much more efficient application that they're trying to use. And then, as always with microservices, you might just have too many. Like, do you really need that many microservices? If you have two systems or two services that are highly dependent or tight dependency on each other, just make them the same service. Do you really need to break those apart? It's again that balance where microservices are really easy to maintain from a developer standpoint, because when you make a change, I only need to update this one little thing, and the test cases and the permutations across them are much slower on a unit testing or integration testing. And so when you make that more of a monolithic single system, it's a little bit harder to test, but the benefits that you see downstream from an environmental standpoint and carbon emissions can offset that benefit for the developer. So again, finding that balance point in between. And then specifically from architecture now into some coding operations, carbon triggering I know was touched on by Jen with the browser extension. Go install that she created. It's really cool. But this is a great concept where I won't touch on it too much. There's fluctuations in the various grids that exist around the world, power grids, and those are based on renewable energy. So when the sun isn't shining, or it's not windy, or maybe your drought and the hydro is a little bit lower, you'll have to offset that with dirtier electrical grids, the coals, the natural gases, the nuclears. And so these fluctuate over time as weather changes, as whether these things change around the world. So understanding where these fluctuations are and taking advantage of them in your software, making your software carbon aware so that it knows in a high intensity time, produce something else for the customer to do. Or you can take a proactive action on this by saying, shifting your workloads to greener regions entirely. If you run, just based on this graph here, if you run your workloads or your machines in Germany or Poland or the UK even, just shifting them to France or Norway or Sweden will save you carbon emissions and not having to change anything about your system apart from, latency. So, again, on that balance between business use cases and compliance and whatnot, if you have the ability to run your workloads in a different country, within Europe or anywhere around the world, that is something that's a very easy step that you don't have to change anything else just apart from where you deploy this, and automatically your carbon footprint and you're running these things in greener locations. So similarly, if you think of that as shifting your workloads in space, physical space or virtual space, it may be, you can also shift it in time as well. So can you delay any asynchronous jobs or batch jobs or anything like that customers don't need immediate responses to? Can you delay those into times where there is a lower carbon intensity overall? So all these things can be built into the software components and pieces of the system. But overall, I think I'm now the third, maybe fourth person in a row to say this, that the greenest system is one that is never built. There's a very similar operation or component here from the operational side where, the easiest system to operate is one that's never built. But those aren't realistic. We still have things, we still have systems that are built. And so finding that balance is really the key, right? And so again, can't go all in on environmental because there's still functions, there's still things that need to exist for people to use and take advantage of. So finding that balance between all three layers of these sustainabilities is the key, and is where you see the most impact across, and where people want to jump in and are able to use these systems and take advantage of them in the first place. And then I'll just do a quick pitch here for the principles.green as well. If you haven't seen this, or I think Asim mentioned it at the start here, please go, if nothing else, start the conversation with the rest of your group, with the rest of your teams. Become a contributor as well on this. It's on GitHub. Pull it, make changes, submit the concepts that you have, help and contribute here. But mostly think about how all of these apply to your system and where your trade-offs are and where you can take advantage of some of these things. That's really, at the end of the day, what we need to start instilling in everybody is making sure that those questions are asked. We may not like the answers today, but ask the questions, and those answers can start to evolve and change over time.